So now I'd like to discuss what rings and fields are. I'm going to assume you're familiar with groups. And so, quite briefly. Um, a ring is an abelian group that has an additional structure defined on it, which is sometimes called a semi-group. It's basically a group without inverses. So what you have is what gets called an addition law. Again, this is just, it's a set equipped with a commutative group structure. And then you have an additional structure on the same set which doesn't necessarily have inverses for all the elements. In fact, in particular, we call the invertible elements in a ring units. But that's not all of the ring. And there's a relationship that has to hold between the group operation and the semi-group operation, and that's called the distributive property. It's the same as the distributive property that holds for integers and real numbers. So like your typical example of a group is the integers. A ring. Your boilerplate example of a ring is the integers because they're an abelian group under addition because they have inverses, and they're a semi-group under multiplication because, well, there's an identity and it's associative, but there's no inverses. The only things that have inverses are 1 and minus 1. And suddenly the terminology of units starts making sense because 1 and minus 1 are in some sense special. At least it's not surprising that we would consider them to be special elements in the ring of integers. Now a field is a ring. It's actually your more straightforward ring. It's an abelian group with an additional group structure defined on this set. So, the real numbers are a ring. It's basically just, okay, so you have your abelian operation like addition, and then your multiplication has inverses for everything besides the additive identity, which that can't really have a multiplicative inverse. There is an exception. It's your trivial ring. Just like your one element ring. If you even consider that to be a ring, it's really just a matter of like how you define things. But if 0 equals 1, then the ring has no other elements, and then trivially, the additive identity has a multiplicative inverse. But in general, a field is a ring where everything but the additive identity has a multiplicative inverse. So it's just like an abelian group that has a additional group structure defined on it, which is compatible with the abelian group under the distributive property. So like there's a relationship that exists between these two group structures on the same set. That's what rings and fields are. And kind of like what you want to study in a group is a normal subgroup. What you want to study in a ring is its ideals. And it's the same thing as a normal subgroup. It's the kernel of a homomorphism. But in this case, it would be a ring homomorphism. So, meaning if you have a function from a ring to another ring, it's not enough that it's a homomorphism on the abelian group structure. It also has to be a homomorphism on the semi-group. If you take a product in, it should be identical whether you take it in the domain or the range. The products, the operation sort of, in some sense, like linear, compatible with the group operations. And in that case, it's not perfectly obvious what's considered one consists of the kernel of the homomorphism, but it turns out that it's the set that maps to the additive identity. It's the set that goes to what we call 0. Because using the integer examples, integers are your favorite ring to work with, and I guess by extension the rational should be your boilerplate, ring. And in that context, the reals arise from like the ordering properties of the rationals. If you want to take like supremums, but like if you want greatest lower bounds to exist in the set, they're almost a topological concept. But the complex numbers are an algebraic concept because they're the algebraic closure of the rationals, meaning the roots of all polynomials exist in the complex numbers, which is also true with like polynomials with complex coefficients, meaning adding polynomials with complex coefficients keeps you in C, and every polynomial over Q has roots in C. That's introduction to rings, I guess. That's what rings are.